All right, wow, the room is really packed. It's good to see so many people who are passionate about this topic like myself. So to start off with today, we're actually going to do a bit of a thought experiment. So in my hand, I'm holding a Rubik's Cube. Puzzle game, hopefully a lot of you are familiar with, might have had one as a child, might have got really frustrated like I did when I was a child and pulled the stickers off and stuck them back on because I couldn't actually solve it. And what we're going to do is we're going to think about the person who's sitting next to us. They have headphones on, so you're not generally talking to them. And what you need to do is you need to visualize how you're going to tell them to solve this Rubik's Cube. You have to look at the Rubik's Cube. You have to look at the way that it's configured and the colors. You have to understand how many you're going to twist and you're going to turn it so that you can solve it. And then you've got to come up with some kind of notation. Notation that will allow you to write down for that person exactly how they're going to solve it. And so you go about doing this and you write down a certain combination, you figure out how to solve the cube. And what happens is that you'll be able to write down a list of sequences for this particular configuration that it currently is now, or the one on the screen, and they'll be able to solve the cube. But now the person on the other side of you that you haven't solved the cube for would like you to solve their cube. And their cube is in a different configuration. And so now you need to figure out again, how do I twist and turn the cube, and how do I solve it for them? But this is a 400 level talk. That means a lot of people in the room are developers. And there might be also some other people who've come along just because it's artificial intelligence and that's a buzzword. That's okay. So you think, what happens if I had to solve the cube for every single person in the room? Well, I'm a developer. I'd sit down and I'd start to write a program to do that. I have my notation that I had before so that the original person could solve the cube. And now, what I'm going to do is write a program to do that same thing. So the person comes along, they input the different movements that they need to do in the cube so that they can solve. And then we write an algorithm, or we crunch the actual result so that they can solve the Rubik's Cube. And you think about this for a while and you think, well, it's a 3x3 cube. There can't be that many combinations. Start to do the maths on this. So there's 9 squares on each face. You can actually twist the cube. You can't twist the center, you can only twist the outside, which means you have 3 tiles that you can twist on each face, which means you've got 12 tiles on each of the rows. You have 3 rows, so it's 3 times 12, plus whichever way you decide to actually pick up the cube and turn that face. So 8 factorial times 3 times 12. And if you actually do the maths of how many permutations there are in a Rubik's Cube, it ends up with this number. That's quite a big number. If you're not used to dealing with big numbers, 43 quintillion. Quintillion, quadrillion, trillion. Hey, but we're developers. This is the age of Moore's law. Your smartphone now has a quad-core processor in it, most likely. Your MacBook is capable of millions of instructions per second. So if you wanted to, you could try and write a program to solve all of the permutations of the Rubik's Cube. You have quite a powerful processor in your pocket or in your actual laptop. If you tried to do that, and someone actually did, first of all, if you minted a Rubik's Cube for every single permutation, it would cover the Earth's surface 275 times. I'm not really sure the governments of the world would like us to build 43 quintillion Rubik's Cubes based on the natural resources that we would use, considering there's only 7 billion people on the planet. And if you did try and crunch that number, it would take you 36 years of CPU time to solve. Somebody actually did this over a long period, buying lots of CPUs from the cloud. And so the problem is actually bigger than we think. It's actually quite hard to brute force. So what we need is another solution. Maybe we should look at the history of some other complex games, and we can decide how would we solve the Rubik's Cube if we needed to solve it for everyone standing in this room. So first of all, we'll start with noughts and crosses, or tic-tac-toe, depending on which part of the world you are from. It's actually arbitrarily solved. 1 with 5 zeros. There's about 20,000 combinations if you follow the rules. Your smartphone can actually churn out all the permutations quite quickly. Then we move over to our friend the Rubik's Cube. He's 10 to the power of 18. That's a 1 with 18 zeros behind it, as we just talked about, which is a quintillion. We move up to checkers, or drafts if you're English. That's 10 to the 20. Then we move up to a common game that lots of people spend a lot of time trying to crunch the algorithm for, which is chess. All of those expert systems and master systems you play in your chess programs on computers. And then finally, the Chinese game of Go. 10 to the 360. We know that we can brute force the Rubik's Cube in 36 years. People have attempted to brute force the checkers game and have only got a part way through. They spent about 18 years doing it, and it's partially solved. There's a phenomenon in our solar system where the sun heats up, which gives us atmosphere, which keeps the Earth alive. They predict in about 100 million years the sun will run out of heat power, meaning that the Earth will go cold and it will become like Mars, and we call that the heat death of the Earth. With the current computing capacity and even the trends that we see in Moore's law, it will actually take longer than the heat death of the Earth to brute force the game of chess with our current capacity, unless we do something very different in technology. That also means with something like Go, which is infinitely harder, that we cannot actually solve all the permutations. These are the games that we've managed to brute force. Tic-tac-toe and the Rubik's Cube and a few others that are a bit more obscure. We got to 10 to the 14 with checkers, so partially solved, and it took someone 18 years of doing it. And so we need to think about a completely different way to solve this problem of the Rubik's Cube. So we lay down in the grass and we think about it a little bit, us Amazonians. How do people currently solve this problem? If you think back to 1996, there was a program called Deep Blue, that was done by IBM that actually bet Garry Kasparov at chess. It obviously didn't brute force the solution because we can't brute force chess. It was actually the last major attempt of brute forcing something on a complex game. They actually built custom hardware, and the hardware could actually compute 200 million chess moves per second. To give you an idea why that's so significant, the current chess engines today that play on master level and play against people like Garry Kasparov process about 2.5 million moves per second, and yet they can beat some of the highest ranked players in the world. And so they have found another way to actually solve the game, involving search algorithms and things called alpha-beta, which is used in chess. Last year, Lee Sedol, the 9th Dan Go player, was beaten by a DeepMind computer called AlphaGo from Google. Same sort of thing, except they use deep learning technology to be able to beat the 9th Dan, one of the best players in the world. And so instead of brute forcing our way through the Rubik's Cube, perhaps we need to use one of these mechanisms. If you think about back to our Rubik's Cube problem, the first thing we had to do was see what configuration it was in. If we did not know the state of the Rubik's Cube, we could not solve it. That was either arbitrarily through the program where someone's entering it, or we just look at it with our vision. The second thing is you need some way to communicate to the actual person next to you how to solve that Rubik's Cube. And finally, you need to actually know that someone has actually got the configuration and they can solve the Rubik's Cube by following your instructions and telling you that it's done. So what we're going to talk through today are some services that we have released that help you solve these problems. First off, we have Amazon Recognition, which is image recognition. We have Amazon Poly, which is text-to-speech. And finally, we have Amazon Lex, which is a conversational interface used to build things like chatbots. And if you're interested in the topic of chatbots and using Lex more, This afternoon, Alex Smith, your MC of this track, will actually get up and do a whole talk on how to build a chatbot with Amazon Lex. So first off, let's start with recognition. So it will recognize objects as well as people, as well as common sceneries. 83% outdoors. It's a person. He's riding a bike. It's a mountain bike. You'll notice when you actually do image recognition that you don't get this is what it is. You get a confidence level. And so all of these deep learning models that you'll use when you're trying to do image recognition will actually give you a confidence model that's generally a percentage. Here's one of a face. So we're pulling out parts of the face, we're detecting it's female, we're detecting their eyes are open, and we're detecting that they're happy and they're smiling. Now you could go and build one of these yourself. There are many open source libraries, including OpenCV and a few others, where you can actually build this type of model. Scientists at the University of Berkeley have figured out that to train an image recognition model with enough data points to actually detect these types of two pictures at that kind of confidence rate will take you about 10 to the power of 12, which is 1 trillion data points for you to be able to train it to get this type of confidence level. So most companies don't have a team of data scientists, don't have thousands of cores of CPU running around, and definitely don't necessarily have the business problem to actually invest all of that to do image recognition. There are some companies that do. So BlackRock, the huge hedge fund, they actually use image recognition to look at all the satellite images of car parks in big malls in the US. And instead of looking at the financial reports of those companies, they count the number of cars in the car park. And that's how they figure out whether they're going to buy or short that stock or what the stock price should be of that stock, based on how many people are turning up to each mall. We can also do face recognition. And in a minute, I'll show you a demonstration where we're going to get recognition to recognize my face and let me into a house. You can see here that the poses are completely different. It will also work with different ages to a certain degree. We've got 98% here. Next up, we have talk. So if I know that there's an image, if I know that there's a person in it, how do I convey that message to the end user? So what we're going to do now is switch to a demo and use these two services. Excellent. Okay. So what we're going to do here is we're going to run a little Python script. This Python script is going to call the image recognition software. It's going to take a photo of myself from the Mac photo booth app. And then it's going to tell us what it detects.
Please point your external webcam at the subject.
Back.
Taking a photo.
Okay, it's quite dark. It's probably a bit sad that there's 25 spotlights shining in my eyes.
I detected the following labels: person,
okay, so it's detected
human, portrait,
I'm
selfie,
a person, I'm a human,
and head.
I'm taking a selfie, and I've got a head. That's pretty good.
I can see one face.
I am wearing sunglasses.
A person is male.
So
He
you
is
can
wearing
see by the
sunglasses.
difference in
He is smiling.
light
He
from
looks
what
happy.
the photo booth sees to what it just snapped off the command line with so much light glaring off the top of my head. Guess lucky I'm not bald. Then it's decided I'm wearing sunglasses, I'm smiling, I look happy. How this is actually working in the background. This is the metadata that it's actually pushing out when it detects the photo. You can see the confidence levels here. Oops. You'll see that selfie only just made it at 62%. So anything under about 58% will get cut off the bottom. It detects that I'm a human. That's also pretty good. And then we actually have a lot of different labels that we put in and really detailed confidence levels in case you want to feed this into another app and you want to do something with this data. I have a left eyebrow, that's good. I also have a right eyebrow. We have the metadata response. And then the other thing that we do is we send a second part into the API. And what that is actually doing is this green square that we saw before. It's detecting the face. And then it's pulling out, am I smiling? What emotions am I feeling at the moment? Am I wearing sunglasses? No, I just got punched in the head by 25 spotlights. Okay, so that ties the first two together. And we could now write a program with our Rubik's Cube that took a photo of the Rubik's Cube. We would have to do it 8 times because it has 8 sides. It would be able to go through some algorithm that we would build, and then it could actually say to someone, how do you need to twist the Rubik's Cube to move on? Back to the slides, please. So you would have heard Polly coming through. There's 26 different voices in Polly. None of them sound like me, my accent. You can configure Polly to do text-to-speech, you can configure it to do pauses, and you can configure it in the different languages. What I've actually done when we were going through that demo is it's literally, have we detected sunglasses? Is it a male? Is it a person? So I've actually, when there's high confidence return in those tags, I've actually told the system to read those things out. Polly doesn't natively read out all of the things that are returned by the recognition API. But this is the age of the Internet of Things. Doing a demo on my MacBook's not really going to satiate all of you users in here. This is the age of development. We all need to have Raspberry Pis and IoT and smart cities and all the other things that are plugged in. So I'm going to up the ante now. I'm going to switch back, and now I'm going to do a demo with this. Recognition, Polly. I'm also going to use a little bit of Lex, but I'm not going to go into the details of Lex because you'll be able to dive into that with Alex later. So I've got a Raspberry Pi here. And I've got a camera plugged into it. And so it's actually going to act as our real-world sensor. And the problem we're going to solve here is I own a house. I'm renting it out on Airbnb. But the thing that frustrates me the most when I rent things out on Airbnb is that people say they're going to turn up at 1 p.m. and collect the keys from me, but their plane gets delayed or they just don't notify me, and they turn up at 5 p.m. So I've got to structure my entire day around the fact I have a renter coming. So how about I build a system with recognition and with Polly, and what I do is when the person actually rents my Airbnb house, I get a high-resolution photo from them, and I have an automated door lock. And when the person turns up to my house, they're going to scan their face, and then I'm going to automatically open the door, and it's going to notify me that a person has turned up and has started renting my Airbnb house. And then from there, this is the age of the Internet of Things, so we can put in how much water did they use, how much power did they use. And also from a security point of view, when they leave, we can also switch the lock off and lock them out. So, if we switch back to the laptop, please. Okay. So I have an AWS IoT Internet button. They're generally programmed to buy something off Amazon.com. We won't be doing that today. This is going to act as the virtual doorbell. My Airbnb person has turned up. For this next part, actually, I might call my assistant up here, your favorite MC, Alex Smith. I feel like I need some shielding from the 25 spotlights that are shining in my eyes while I take this photo. Where is he? He's left me. All right, we'll try without him. I have a volunteer. Okay, so what I'm going to do is I'm going to press the Internet of Things button. It is going to go through the internet. It is going to set off a series of events. Maybe not. Maybe I'll press the doorbell again. No one's home. My 4G network failed me. All right, that's okay. We're techie people. I'll just fix it manually. Publish to topic, capture photo.
Hello. Please look at the camera. Remember to remove your glasses if you are wearing any. 3, 2, 1, and click.
I don't know why
Please
they make
wait a
doorbells so
moment.
short.
Nope. I could not find you on the expected guest list. Go away.
All right.
I'm back. Fine, I get to go on stage.
I can't hear myself speak.
I can hear you speak.
Okay.
Oh,
Hello.
hello.
Please look at the camera.
Please look at the camera.
Remember to remove your
Oh,
glasses
this
if
is a
you are
bit like
wearing
working
any.
out.
3,
3,
2,
2,
1,
1,
and click.
All right.
Please wait a moment.
Please wait a moment.
You will receive an SMS with
receive an
passcode
SMS
shortly.
with passcode
Please
shortly.
stand
Okay.
by.
So we've taken the photo, and now we'll receive an SMS. Because my 4G is failing me, I'll just cheat and go into my DynamoDB table, where I'm also writing the PIN number, which just updated. 9565.
A passcode has been sent to your phone.
Passcode has been sent
Please
to your
read it
phone.
out aloud.
Please read it out loud.
9565.
Welcome.
Welcome.
You may enter now.
You may enter now.
Okay, so I got into my house. So what I'll do now is I'll show you actually how this is set up. So first of all, this is the first demo that we did without the IoT. It's a very simple Python script that uses OpenCV to take a photo from my MacBook camera. And then it calls out to recognition and uploads the photo. We're using the voice Joanna from Polly, who's the person you would have heard speaking back through your headphones. And really what I'm telling Joanna to do is pull all of the labels, so the detect labels out of Amazon Recognition, and speak them back to you. So here's the verbal labels. You can hear the things that were actually called out. I'm a person. I'm wearing sunglasses. I don't have a beard. And finally, we actually saved the picture. So if you were doing automated verification, if you had something like an Amazon Alexa, you could actually build a skill now where Alexa says, I detect someone at the door. Would you like to let them in? And you could say, based on that photo that was sent to your phone, yes, I would. And she would add them to a whitelisted database so that you could now add that person into your house. Might be your relatives or someone who comes to pick your kids up from school. The second image that we saw was my head, very dark, with a green box around it. This is called the bounding box. This is how we detect faces. It won't just detect a single face. I could take a photo of you now and try and detect the faces out of the crowd. We actually did this in Sydney Summit last week, and we took over 10,000 faces. We had a whole bunch of Raspberry Pis connected up with the same cameras that I'm using here, and we had them all around the booth. So we took 10,000 unique faces, and then we built some sentiment. How many people were smiling? How many people were happy at the summit? How many people looked angry? What was the percentage of males and females? And so by using this type of technology, you don't just solve problems for yourself, like the door lock, you can also solve them for your company. If you're in advertising, if you own malls and you want to target ads at people because you can see people walking around your shops and seeing if they're happy. And so you can generally take the mood of the room with this. The second part that we looked at, which is actually the Internet of Things device, so the Raspberry Pi, which uses C, it's actually got 4 simple functions. Capture photo, what happens if it fails, update the passcode, which you saw, so that was the passcode I spoke into the microphone, and then ask secret, so making sure that the secret actually works. The main part of that code is really the speaking side. And what the speaking side is doing is not just using Poly to actually talk to you, it's also using the Lex service. Because if I'm speaking those numbers in, there needs to be a service on the other end that will do natural language processing, so another pillar of current AI research, and converting those to the numbers that we can upload and then allowing the lock to unlock. So that's a very simple demo of Lex. I've only using it for a few lines. And then we can dive into Lex later on with Alex, who's going to do a whole chatbot-orientated demo around that service. Okay. Here's what the setup looks like. It's all wired into the front of my thing here. I was going to pick it up and show you, but I figured that I'd break it, so I didn't. So instead, I've taken a picture of it for you. It's a Raspberry Pi with a camera on top and a Wi-Fi dongle. We talked about the here part. So this is really Lex and natural language processing. It's a conversational interface. In this case, I just used it one way. It's actually the thing that powers Amazon Alexa. So if you've heard of the Echo Dot, the Amazon Alexa, this is the underlying technology behind your Alexa. When you ask it what the weather is, when you ask it to play songs, it's exactly the same technology that you're using in Lex through the API that powers Alexa. I would like to book a flight to Hanoi tomorrow. To actually process this sentence, we need to break it up. Computers don't speak the way we do. They speak ones and zeros. So first of all, we need to figure out what the intent is. If you go to any of your personal assistants today, you'll have to say, play a song, or I want to know something, or what is something. And so what they're doing is looking for the intent. What is the trigger word? What is the thing I am trying to do? The where. So we need to know where Hanoi is. We need to be able to look it up on a map. We need to be able to see what it's close to, how far away it is from your current location. And finally, the when, so tomorrow. So we need to know the current time and date to plot when tomorrow is. So that is a basic overview of See, Talk, and Hear, and the Amazon services that we released at reInvent last year. We have gone through a lock demo where we can do face recognition, and we're also using Lex to push out a security code. We're doing See, where we're taking images and recognizing people's faces and their mood. But what else is there? There actually is one other pillar of current artificial intelligence. There is image recognition, there is natural language processing, there are things like text-to-speech, and the final one is robotics. So here is our founder, Jeff Bezos, in a robot at our Amazon Mars conference a couple of weeks ago. We have been using robotics in Amazon for a long time. We purchased a company called Kiva Robots. We now have thousands of these going around our warehouses, picking up pallets. And so we are also investing heavily in robotics technologies and how we can drive robots and autonomous vehicles. In fact, we've been using AI at Amazon for a very long time. Here's our website in 1996. We've probably changed the way that we do design a little bit. But what you'll actually notice is in these two boxes, personalized notification service and a personalized spotlight, We're actually using AI back in 1996 on our website to recommend books to you. This is our new building in Seattle. It's called Day One. The binary code that you see at the top actually says Day One, and a lot of our buildings have this binary code imprinted on their wall to remind us that this is day one of the AI, of the deep learning revolution, the things that we've currently seen, such as AlphaGo, beating the Go game, some of the image processing that you're seeing now, that we are now giving you access to. And so we're investing heavily in this, so we've been in it now since 1996, but we're still continuing, and it's still day one. Right now, there are several things that people would like to do in this crowd, I imagine, that current services from any cloud provider can't provide. And so we are investing through hearing with millions of echo devices, hearing natural language, hearing different accents, using them in different regions and how people want to talk so that we can improve our algorithms. And you can use this technology just like the big corporations use this technology, without having 5 data scientists, without having 1 trillion data points that you need to train the model on. We are improving our vision technology. Our Amazon Go store, it's checkoutless. It actually watches people, tracks people walking around, picking items off the shelf and adds them automatically to your cart without any kind of checkout and just charges you for them. We are training our robotic models with our drone services deliveries. Our first drone delivery started kicking off in Cambridge at the start of the year. So now we're doing drone deliveries in the UK. So you don't need the last mile anymore. And finally, we're all pushing towards this, general intelligence. So everything that I talked about today is specific AI trained to do specific things. And most of the deep learning that you'll see in the field at the moment is all around specific intelligence, artificial intelligence. General intelligence is more how we think. We can give any problem. We can look at the Rubik's Cube and we can problem solve about how to actually change that. Computers cannot do that. The models that we train today can do the one thing. They can play chess really well. They can play Go really well. They can detect faces really well. And so what we need to do as an AI community is build out our technology so that we can do general intelligence, and we can slowly develop algorithms and data sets that allow us to do general applications of artificial intelligence and not just specific ones. Oh yeah, and our Rubik's Cube. Here's what happens if you apply deep learning to a Rubik's Cube. I'm not going to show you any more than that, but as you can see, it got solved in a very short amount of time. Tonight, for the closing keynote, Olivia Klein, who you already seen talk this morning in serverless, is actually going to get on stage and talk about how to solve that Rubik's Cube with deep learning, with algorithms, and the little video that I just showed you there, where they're solving it in 637 milliseconds. That is the type of thing that we can do when we apply deep learning to these problems, as opposed to doing the brute force that we talked about at the start, which would take us 36 years and cover the Earth 275 times in all the permutations of Rubik's Cubes. That is AI on Amazon. I am Shaun Ray. Thank you very much.